In Lesson 6.4, Arc Length and Surfaces of Revolution, we'll conclude our exploration into plane regions, finding the area of plane regions and all that good stuff, and also our exploration of solids of revolution. Remember, we looked at the disk and washer methods, we looked at the shell or cylindrical shell method. Well, this is going to conclude all that. We're going to be looking at arc length, which is exactly what it sounds like. It's just how far one has to travel along a certain edge from one point to another. Of course, if it's a straight line, we can just use the distance formula. But these aren't going to be straight lines. These are going to involve different kind of curves and arcs. So we'll find those lengths. And then finally, we'll conclude by looking at those solids of revolution again, except this time, instead of looking at the volume of those solids, we'll actually look at the surface area of those solids, which is also very important. If you go back to your geometry days, you'll remember the difference between volume, how much goes into that solid, versus surface area, which is how much goes around the solid. So those are the two big topics here in Lesson 6.4. Without further ado, let's go ahead and take a look at the formula for arc length, which might look very, very familiar to you in a weird and calculus kind of way. Let's take a look now. So without getting into any of the further discussions or derivations of this, let me just go ahead and give you the definition of arc length. That is the arc length formula, if you will. The arc length S is simply going to be the integral from A to B of the square root of 1 plus our derivative of our function, which we will then need to square, and then dx. It really is that easy. So if we're given the function, all we have to do is differentiate it, square the derivative, and then plug into our formula and take it from there. Now you might be wondering, how could it be that easy? Where does this come from? Does it look familiar at all, as I said that it might? Well, let's begin with a very, very simple arc length. And this is going to be the length of a line. In fact, let me go ahead and say that we have a point here that we'll call x1, comma y sub 1, and a point up here that we will call x sub 2, comma y sub 2. Now, you should be more than familiar with how to find the distance between those 2 points, which would equate to the length of this particular arc, although it's a line. This distance will simply be the square root of the difference in the x's. Of course, we'll need to square that, added to the difference in the y's, which we'll also need to square. Of course, this comes from the Pythagorean theorem, which is simply c squared equals a squared plus b squared. And you can see, or you should already know, how that all works out. Well, let's deal with something a little bit different here. Let's deal with an arc. And in this arc, if we want to take this from A to B, of course, there really is no x2 minus x1 or y2 minus y1. So how in the world are we going to do this? Well, what we're really going to do is split this into an infinite number of very little bitty line segments, an infinite number of them. And what we're going to do is find the length of each one of those line segments and then add all of them up. Could it really be that easy? I'm going to argue that actually, yes, it can. Let me take one particular little line segment, this one right here. Let's say that the x2 minus x1 is obviously going to be very, very, very tiny. Let me just call that dx. It's an infinitesimal change, actually. And then that the y2 minus y1 is also going to be an infinitesimal change in the y direction. Let me call that dy. And so if we're trying to find the length of this little line segment, really all we need to do is say, well, the length of that little line segment, which I'll call ds, I can square that, and that will be equal to the sum of dx squared plus dy squared. And there it is. It's the Pythagorean theorem. Problem is that only applies for that one little bitty line segment. So let me play around with this a little bit. If I divide this entire equation by dx squared, what I'll end up with is ds squared over dx squared. this dx squared will actually just turn into 1, and over here I'll have dy squared over dx squared. And you might already tell that we're kind of heading in an interesting direction here. I can go ahead and keep this all squared, but I'm actually going to rewrite this a little bit. I'm going to call this ds over dx quantity squared. And over here I'll have 1 plus, well, if we have dy over dx squared, I could write it that way. Just pull the squared out and apply it to the whole thing. But dy over dx, what is dy over dx? And you might say to yourself, well, that's really just the derivative of a function. And if that's the case, then let me keep my left side the same, ds over dx quantity squared. Over here, this will just be 1 plus the derivative of y, whatever that is, squared. Well, now, this is getting very interesting. Maybe you can see where this is all going. If I go ahead and square root both sides, I'll have ds over dx equals the square root of 1 plus the derivative of this function squared. And hopefully you can see this last step. I'm just going to take this dx, multiply it on both sides, and there we go. My one last step here is that's going to give me the length of one little bitty line segment. As I said, we want to add all of them up. So let's go ahead and integrate on both sides. And if we do that, what's going to happen? On the left side, we'll just have s, and on the right side, we will have that magic integral that we wrote in the box up above, 1 plus the derivative of the function squared, dx. Now, if I integrate that between a and b, that will give me my arc length, and that is what I've been looking for. So, hopefully, deriving the arc length formula actually makes a lot of sense. It's really just Pythagorean theorem, or if you will, the distance formula, added up for every little bitty line segment that composes this arc or curve. That's where it comes from. And now with example A, let's see this thing in practice. So here in our first example, I've gone ahead and graphed the function y, and you can see that graph here. And I've also highlighted the part of this curve which we want to find the arc length of. That is between x equals 1 and x equals 27. You can see it highlighted here. If you cannot see it highlighted, there's x equals 1, and there's x equals 27. So we want to find the arc length of this curve between those 2 points. Well, this really is not a very difficult thing to do. The very first thing we need to do, of course, is simply to differentiate this function. And this is a very easy derivative to do. In fact, if we do it correctly, we'll just get x to the negative 1/3. Now, once we've done that, we do need to go ahead and square this function to stick it into the arc length formula. But that also is not too difficult. That will simply be x to the negative 2/3. And now we can go ahead and set up our arc length formula. It will be the integral from 1 to 27 of the square root of 1 plus the derivative of the function squared, which we've already done, and then dx. Now, this could be a very fun integral for you to play around with. My advice to you is to factor out x to the negative 2/3. Divide both of these by that and pull it out of the integral. If you do that, you can then set up a u du substitution where u is x to the positive 2/3 plus 1, and then du would, of course, simply be 2/3 x to the negative 1/3 dx. So you can go ahead and factor out x to the negative 2/3, do your u du substitution, work it all out. I'm not going to do it here. You should be very confident and very capable of doing that yourself by now. And if you do this correctly, what we should get for our arc length is going to be 10 radical 10 minus 2 radical 2, which is approximately equal to 28.794 units. Now, if you were not able to factor out this x to the negative 2/3 and do your u du substitution and all this fun calculus stuff, you could, of course, run this entire integral through your calculator, whether you have a TI 83 or 84, or 89, 92, or a Casio or an HP, whatever you have. Your calculator should have the capabilities of doing a definite integral. And so if you do go ahead and run this definite integral through your graphing calculator, it should return to you an answer quite like 28.794. So there you go. That is the distance, the length of this arc. I do challenge you to see what would happen if you tried to find the linear distance between these 2 points. I posit it would be very close to this arc length, but not exactly the same. So the calculus saves us once again in a fun and exciting example. And with that, let's try one more example of arc length, example B, where we're actually going to end up with an integral that you don't know how to do by hand. So if you weren't able to run this one through your graphing calculator, read up on your user's manual or do some quick research, because that's the only way you're going to know how to do example B at this point in time. Let's go ahead and take a look at how evil example B looks. Wait a minute, did I just say that example B was going to be evil? This doesn't look bad at all. It's simply a quadratic function, and we're just trying to find the arc length between its 2 zeros. How hard could this be? Well, here's the thing. I never said it was going to be hard. I just said we wouldn't be able to do it by hand. And let me show you why. If we want to set up the arc length formula for this, of course, the first thing, once again, that we need to do is find the derivative, which is just y prime equals 2x plus 1. If we want to go ahead and square the derivative, let's see, that's just going to be quantity 2x plus 1 squared. And, of course, if you want to write it out, you can. This isn't really all that necessary. But if we do write it out, it looks like we're going to end up with 4x squared plus 4x plus 1. Whatever, no big deal. If we go ahead and set up our arc length formula then, it will be the integral between negative 2 and 1 of 1 plus this thing. So it looks like really what we're going to end up with is 4x squared plus 4x plus 2, all under this radical. Now, I invite you to come up with whatever method you like at this point to evaluate this integral. It can be done, I'm not saying it can't, but we haven't learned how to do it just yet. So my advice, run it through your graphing calculator. It's simply a definite integral, and if you do that correctly, you should end up with this arc length being about 5.652 units. That's how much space is traversed between the 2 zeros of this parabola here. 5.652. Of course, the linear distance would just be 3, but because of the bend there, it does bend quite a bit, and there we go. There's our arc length. So I never said this was difficult. It's just that there are times when we haven't learned how to evaluate the integral just yet, and in those cases, feel free to use your graphing calculator to evaluate the definite integral yourself. And there we go. Not too bad. All right, well, the last 2 examples of these notes are going to involve surface areas of solids of revolution. So before we get to those, let's go ahead and look at the formula for the area, or surface area, if you will, of a surface of revolution. It also, just like the arc length formula, makes a lot of sense, is not too bad, but in this particular case, I'm going to present it to you without derivation or proof. So without further ado, let's go ahead and take a look at the formula for the surface area of a solid of revolution. So again, unlike the formula for arc length, I'm not going to show where this formula comes from, but I will explain just a little bit about what it all means. This is going to be the formula for the area of a surface of revolution. A surface of revolution is nothing more than the outside part of the solid of revolution. It's the surface of that solid. And so what I want you to do is I want you to consider a bunch of circumferences, circles, if you like, circumferences of the discs or washers, or even the outside surface area of these cylindrical shells. Either way you want to think about it, what we're going to end up with is 2 pi times the integral from a to b, of course, times the radius of our surface of revolution, times the height. Now, the height of our surface of revolution, this is going to be quite interesting, is actually just the arc length formula. So, if you know the arc length formula, the surface area formula is not too big of a stretch. We simply have 2 pi RH. Once again, 2 pi RH. Except this time we're not finding the volume inside like we did with the cylindrical shells. We're actually finding the area around it. And for that reason, the h part of this, the height, is not a constant height, but rather a height that changes in line with the function itself. And the radius is not actually going to be anything difficult to come up with. The radius is simply going to be the function itself. So you can see that the radius and height are both dependent upon the original function, but that the surface area for the solid of revolution is still just 2 pi times the integral of the radius and the height. The height itself just being the arc length. If you like, what you can think of it as is taking this arc length and just rotating it all around the axis of revolution. And then, of course, it would come back on the backside and look like this. So essentially, we're just taking this arc length and rotating it, and that will give us the surface area of our solid. Pretty cool, pretty useful, not too difficult. Well, let's take a look at a couple examples. I'll let you judge the difficulty, but I think you'll agree with me. It's not too bad. Here we go with example C. Alright, so in this example, we're going to take the region that I've graphed for you right here. It's bounded by the graphs of y equals 2 radical x, y equals 0, and x equals 3. That's this region. And what we're going to do is revolve it around the x-axis. Now, of course, by doing that, we're going to end up with this, maybe once again, paraboloid-looking shape. I'm not the best drawer in the world, as you know by now, but it might look something like that. In fact, what I can do is I can show you exactly what this surface will look like. Here it is. It's kind of a wireframe model. But if I rotate it around, you can see how it spins and rotates. And also with this, I can peer inside to this surface. But in the actual problem, there will be a cap on this. So it will be essentially solid, and I won't be able to look inside. But that's what this thing looks like. So coming back to the math of this whole thing, here's my picture. And what we're going to do is try to find the surface area of this entire surface, including the end cap. So to do this, of course, what I need to do is begin by differentiating our original function, 2 square root of x. And if I do that, that's just going to give me x to the negative 1/2. Now, if I go ahead and square that derivative, that, of course, will be x to the negative 1. Or if you like, we can call it 1 over x. Either way, it's going to work out the same. So let's go ahead and set up the surface area formula here. That's going to be 2 pi times the integral from 0 to 3 of our original function, 2 square root of x, times the arc length, which is 1 plus 1 over x, or however you like. Now, I could simplify this quite a bit. I could call this 4 pi times the integral from 0 to 3. If I multiply these two radicals together, it will simply be the square root of x plus 1 dx. And that is very, very doable. If I turn this into 4 pi from 0 to 3, if you don't see it right off the bat, maybe we could call this x plus 1 to the 1/2 power dx. And now it's a very, very simple integral for you to evaluate on your own. If we do this, we'll then have to, of course, add the end cap, which is really just a circle with radius of 3. So I'll just put plus 9 pi there. And for lack of a better description, I will just call that the end cap. All right, so that all works out just fine. If you do go ahead and evaluate this integral by hand, you can do this without your calculator. You can certainly do this by hand. And if you do, what we should get is 56 pi over 3. If we then add the end cap to that, what we should get is that this thing has a final complete surface area of 83 pi over 3. Now, if you did this using your calculator or you wanted to decimalize it, this should come out to about 86.917 square units. But again, you should have been able to do all this by hand and come up with the 83 pi over 3. So you see, it's not really that difficult of a thing to do when you're able to do it by hand anyway. In our next example, example D, we're again going to get an integral that is not elementary. We won't be able to do it by hand, and that actually makes the problem quite a bit easier because the calculator will take care of everything. Let's go ahead and take a look at that one right now. So we'll finish out these lesson 6.4 notes by taking a look at one last surface area problem. What we're going to do is we're going to take the graph of x equals 1 over y squared. That's the graph that I have drawn for you here. But we're only going to look at the part of this curve between y equals 1 and y equals 3. And so that's the part that I've highlighted for you. And what we're going to do is we're going to take the region bounded by that and the curve, if you like, x equals 0, and we're going to revolve that around the y-axis. And when we do that, what we should end up with is a surface that looks more or less like this. It's almost kind of like a funnel, if you will. So what is the surface area of this funnel? Well, we know our original function is x equals 1 over y squared. The first thing we need to do is find the derivative of that function. And so x prime is actually going to equal negative 2 over y to the third. Now, if we go ahead and square our derivative, of course, what we'll end up with is 4 over y to the 6th. And now we have everything we need to set up our surface area formula. Our surface area will be 2 pi, and we'll go from 1 to 3. Notice that everything now is in terms of y. So we're going from 1 to 3 in this direction this time, from 1 to 3. Our original function is 1 over y squared, and then we'll do our arc length function, which is 1 plus 4 over y to the 6th. And again, everything is in terms of y, so there's our dy this time around. Now, you can do whatever you like to this integral here. I was not able to find a way to set this integral up in such a way that I can evaluate it with the knowledge that we currently have. We'll learn how to do integrals like this later. But for now, my suggestion is simply run it through your calculator and see what you end up with. My calculator gave me 5.516 square units as the surface area of this revolution. We didn't have to worry about end caps here or anything like that because those were not involved in the region. The region was simply bounded by the y-axis and this curve. So there were no end caps or anything like that. And there we go. It actually gets quite simpler when we're not able to evaluate the integral by hand because we have to default to doing it in our calculator. And that is fun and exciting. And so here in lesson 6.4, we've covered two very important topics. The first was arc length. Given a curve or an arc or whatever you like to call it, even a line, all we're going to do is decompose that curve into a series of very, very, very short line segments. Once we've done that, we'll use the distance formula to find out how long each line segment is. In truth, the length of each line segment is actually infinitesimal, but we'll use the distance formula anyway. And once we've found the length of each one of those little line segments, we'll just add them all together, and that will give us the arc length that we're looking for. So, as we've done 100 times with calculus so far, it's simply adding up a bunch of little things to end up with the big overall thing. After we did that, we moved on to looking at the surface area for solids of revolution. And again, really all it was a decomposition of that surface area into a bunch of circumferences. Of course, each circumference had a height, if you will, of an infinitesimal amount. That's why that dx or dy was there. But the radius and the height, if you will, all depended upon the original function. And so after decomposing that surface area into a bunch of circumferences, all we had to do was use an integral to add all those circumferences up, and we ended up with the surface area of our solid of revolution. So the big important thing to remember here, if nothing else, are simply those two formulas that we talked about, the arc length formula and the surface area formula. So remember both of those as you're working on your assignment for 6.4. And as always, good luck.